All right. Good morning, everyone. We are recording. Let me go over a couple things I went over last time. So one of the homework problem, I believe 2.8, is it 2.8 or 3.8? Whatever. I think it is 4. We had t squared minus 1 x prime equal x squared plus t. So x prime is x squared plus t over t squared minus 1. So f of tx is x squared plus t over t squared minus 1. So this is continuous for t different plus or minus 1. Now we know 0, that was x of 0 equal 1. So 0, 1, so this is for t naught. So this is for x naught. So we want t to be between minus 1 and 1. So this 0 is in it. Correct? And so if we look at del f over del x, that is 2x over t squared minus 1. And del f over del x is bounded less or equal to 2x over a squared minus 1, where t is between minus a, and 0 less than a less than 1. So, but x is unbounded, so we need to have x less or equal to some number m. Otherwise, will not be Lipschitz. So your d is all tx. T is between, last time we used alpha, 0 less than a less than 1, and x less or equal to n. So that is your d. And on that d, you have a unique solution. Okay? Is that better?
That's what I was trying to say yesterday. I wasn't sure how X could be Lipschitz and yet be bounded.
What? Yeah,
You answered it here now. That makes sense.
Sorry, I didn't hear you.
Yep. Yeah. X has to be bounded in order to still be
Yeah.
Lipschitz.
So basically, your thing is this is minus a, this is a, and it has to be, this is minus m, and this is n. So this is your d. It has to be bounded. Okay. All right. Any questions? Yeah, I thought about it last time, and I said I think I need x to be bounded, which is very true. Okay. So that corollary is very, very powerful. All right. Any questions? All right. Let me go back to this example. I'll give it to you. I'll give you a minute to copy down. Then I'll move to the. I'm gonna go back to the last example we considered last time. All right. So I'm gonna erase this. Okay. So last time I gave you this example: x prime equals 0, 1, minus 2, x1, x2. And we decided that was this the fundamental matrix? Do you remember? Sine t, yeah, cosine. All right. So that was cosine, sine minus cosine minus sine. All right. So, if we have a 2 by 2 matrix A, B, C, D, then A inverse is 1 over determinant of A, and that's gonna be D A minus B minus C. Okay? All right. So what is the determinant of A? And remember, determinant of alpha A is alpha n times determinant of A, if A is an n by n matrix. Okay, alpha is some scalar. So determinant of phi is e to the minus 2t times cosine square t minus cosine t sine t plus sine t cosine t plus sine square t, and that is e to the minus 2t. These and these cancels, and so the determinant of phi is e to the minus 2t. Now, what am I doing this? Because I need to compute phi inverse. So phi inverse of t is e to the 2t times the matrix. You see, e to the 2t, this is 1 over the determinant. It's 1 over the determinant will be e to the 2t. Will be d a, b, c, d cosine t minus sine t minus b minus sine t minus c cosine t plus sine t and cosine t. All right. So that is phi inverse. Okay. Any questions? So if we look at if we look at the matrix phi of t, phi inverse of S now, and this is phi of t, phi inverse of S. And if I look at this and if I sum all the absolute value, if I sum everything, that will be e to the minus t times 6 times phi inverse of S. That is times e to the 2s. Okay? Oh, sorry. It's times, sorry, this is wrong. E to the minus 2t. This is e to the 2t times e to the minus t, because the matrix phi has e to the minus t. So will be e to the, and so this is e to the t, and that will be e to the s. Again, all right, if I add these, I'm gonna get 6. So this is 6 e to the minus t minus s. There we go. You see how you do it? Okay? Does that clarify things now? So remember here, remember what we need. We needed, okay, for uniform asymptotic stability, we needed phi t, phi inverse of s to be less or equal to m e to the minus beta T minus S. So here, beta is 1 and M is 6. Okay? This is what we showed last time. This is theorem 4.23. This is, we needed theorem 4.2.3. Okay? You see, that's how you get it. So the zero solution of this system is uniformly asymptotically stable. Only by looking at, all right, by looking at the fundamental matrix. Any questions? All right. Okay. I'm gonna erase this. If I get the chance to do a second edition, I may fill in the details for this example because I think the student can benefit from it. All right. This is all I wanted to do with chapter 4. To chapter 4, theorems 4.21 to 4.23, where general theorem regarding the stability of x prime equal ATX, okay, with xt naught equal x naught. So basically, we looked at the fundamental matrix solution. And we saw in the two examples, one of them we guessed or we verified it is because I did not know how to find it because the matrix the matrix A has time in it. And the second example where A is constant, the matrix, so we could find the fundamental matrix. All right. So these were general theorem. So now in chapter 5, okay, I'm gonna skip Floquet theory here. Chapter 5, section 5.1, we will state particular theorem for x prime equal ax when A is a constant matrix. Okay? When A is a constant matrix. So this is why I think my book got a very good reviews because I will do the general cases and then I will look at A being constant matrix and I do particular theorem related to that. So it will help the student understand the concept more. Why here? So because phi can be found by looking at the eigenpairs of A. Eigenpairs mean lambda and its corresponding eigenvector. Lambda is the eigenvalue. Okay? So it all depends on the type of matrix A, and you will get stability out of it or non-stability. So dwell on this for a second. Okay? I will try to finish your exams this weekend, I can promise you. All right, any questions? All right, so let's start flipping the board and see what we can do for today. Okay. So we are in section 5.1. I'm gonna start with lemma 5.1. Let R of t equal to t to the m e to the minus alpha t bigger or equal to 0. M is a non-negative integer, and alpha is constant. Then R of t is less than or equal to some d for d star constant. Okay. Here's the proof. If m equals 0, then R of t equal e to the minus alpha t less or equal to 1, which is d, since alpha bigger or equal to 0, t bigger or equal to 0. Okay? There we go. Now, if m is not 0, then let's take a look at the limb as t goes to infinity, t to the m over e to the minus alpha t. That is the limb as t to the m over e to the alpha t. That is infinity over infinity. That is the limb of t approaches infinity, and tm minus 1 over alpha e to the alpha t, infinity over infinity, t over infinity, m minus 1, tm minus 2 over alpha squared e to the alpha t, infinity over infinity. So what am I doing here? I'm using L'Hopital's rule. And if I keep doing this, then I will get the limb as t goes to infinity of m factorial, all right, divided by alpha m e to the alpha t, which is 0. All right. Okay, so what does that mean? So since r of 0 is equal to 0 and r of t is bigger or equal to 0, for t bigger than 0, and the length as t goes to infinity, tm e to the alpha t minus alpha t equals 0, implies r of t is bounded. That is, there is a d positive, so that r of t less or equal to d. Okay? So the picture is going to be like this. This is r of t, and this is t. It's going to go like this, and then it's going to go down to 0. So there is a d. So this is your d. So it's continuous, and then at 0, it's 0. Let's say it increases, and then but the limit at infinity is what? Is 0. So the function can go like this. This is what it means. So there is a d, so that r of t less or equal to d for all t. Okay? Any questions? All right, any questions? Okay. All right. Now we're going to do some notation. So definition, and this is 5.1. Let A be a square matrix. Okay, we define just a minute. Let me take this example. Hello? Hi, how are you? Okay. Yes, I did. Hundred. Because I did call yesterday and I did set it up, and I'm not sure what's going on now. Okay. Okay, thank you. Should I receive it? All right. We define this spectrum of A as sigma of A equal to the lambda such that determinant of A minus lambda I equals 0. So basically, this is the set of all the eigenvalues. This is the set of all eigenvalues of A. Okay? Now, so this is a notation, mean the real of sigma of A is less than a number C, means all eigen values of A have a real part less than C. For example, if A is 2, 0, 0 minus 3, then this spectrum of A is 2 minus 3, and real of sigma of A is minus 3. Okay? Which is no, sorry, 2. All right? Okay? All right. So this is what it means. Any questions? All right. This is theorem 5.1. Let real of A, sorry, less than C. Okay? Then for any integer m bigger or equal to 0, there exists a positive constant d such that Tm equal to lambda t less or equal to d e to the ct. And this is for all t bigger or equal to 0. Okay? All right, here's the proof. Say lambda is alpha plus I beta, alpha beta in R. That means lambda. Now, if beta is 0, that means lambda is a pure real. Then alpha minus psi is less than 0. Why? Because remember, the real of sigma, they're all less than psi. So alpha minus psi is always less than 0. Okay? All right? So by lemma 5.1, we have t to the m e to the alpha minus psi t less or equal to d, or all t bigger or equal to 0. Okay? Now multiply by psi t, or t to the m e to the alpha t less or equal to d e to the psi t. Okay? All right? So this is by the lemma. Remember lemma 5.1. So for example, when we had, let's say, sigma of A equal to 2 minus 3, then I can take psi to be 2.1. Then the real of sigma of A is always less than psi. Okay? All right? Okay. Now, any question about that? Okay. Now, let's assume beta is not 0. That is lambda is alpha plus I beta. Then t to the m e to the lambda t equal to t to the m e to the alpha plus I beta t. Okay? And that is t to the m e to the alpha t times e to the I beta t. But that is 1. This is 1 in magnitude, e to the I beta t. Why is that? Remember, e to the I theta is cosine theta plus I sine theta. And remember, e to the I theta is cosine theta plus I sine theta. That is cosine square theta plus sine square theta, square root of 1, that is 1 from Euler's number. So that is 1. So this is t to the m e to the alpha t, which is less or equal to d e to the psi t by the lemma. Okay? This is since alpha is less than real of sigma of A, which is less than C. All right. So this complete the proof. All right. Any questions? So now we're ready to state our next theorem regarding the eigenvalues. All right. Theorem 5.1.2. Let lambda be an eigenvalue of an n by n matrix A with real of sigma of A less than C. All right. Then any solution of 5.111, this is x prime equal ax. And this is 5.1.1. Then any solution x of 5.1.1 satisfies x of t less or equal to d eta ct for all t bigger or equal. Okay. All right. Let lambda 1, lambda 2, lambda k the eigenvalues of A. Okay. Now, these could be multiple multiplicity. So we have multiple multiplicity. So we may have to use the notion of the generalized eigenvectors. Then solutions can be written as xj equal t to the m equal t to the m e to the lambda n t, okay? And j equal 1 all the way to n. All right? So remember, these are separate solutions. We can write them like that. All right? This will be generalized solution. Okay? Then by theorem 5.1.1, we have xj less or equal to vj e to the ct for vj are constant. Okay? Then the arbitrary solution of x is x equal to c1x1 plus c2x2 plus cnxn. Okay? Then for t now, for t bigger or equal to 0, we got x less or equal to c1 x1 plus cn xn. But each one of them is less or equal to each one of them, remember, less or equal to c1, okay, v1 plus c2 v2 plus cn vn e to the ct. Okay? And that basically complete the proof. Guess what happened next? If this c is less than 0, right? So let's say I have the matrix now, -1, 0, 0, -2. So sigma of A is -2, -1. So let's take C equal minus 0.9. Then the real of sigma of A is less than -0.9. So that will be here. -0.9, that is negative, so the solution will go to 0. So this is where we are heading. You see where we're heading? So that will be our next problem. All right. Any questions? We're just trying to build a little bit at a time. You know, 5.13. Let lambda I equal 1, 2 to k be distinct eigenvalues of A where lambda I has multiplicity n I and n1 plus n2 plus n k equal n. You add them up. All right. For example, I will give an example later. If real of sigma of A is less than C, then there is a positive constant D such that e to the AT less or equal to B e to the CT for all t bigger or equal to 0. Okay? Okay? So for example, let's say we have a matrix sigma of A equal to 1, minus 1, minus 1. So lambda 1 equal 1, lambda 2 equal minus 1. So here n1 is 1, here n2 is 2. So n1 plus n2 is 1 plus 2 equal 3 because you're supposed to have 3 eigenvalues. You see? You see what happened here? Okay? So this 3, this is the number of eigenvalues. All right? So this is how it works. Now the proof is similar to the theorem we just did a little bit ago. So I'm gonna skip it. Okay? The theorem is, the proof is very long because it involved the exponential matrix, the Potter's algorithm, if you like. I decided to do it that way. So I'm gonna wave my hand and ask you to read it. All right? Okay. Any questions? All right. So here's another theorem that will summarize everything. Okay. All right. Here's the theorem. Okay. So we're gonna assume that every eigenvalue of A has a non-positive real part and the eigenvalues with zero real part are simple. Okay, this is one. Then e to the at, this is in the norm, less or equal to d for t positive. Moreover, if x is a solution of 5.11, okay, with x of t naught equal x naught, then it's bound. Then it is bounded and the zero solution is stable. Two, if real of sigma of A is less than zero, then the zero solution is asymptotically stable. If there is an eigenvalue of A with positive real part, then the zero solution is unstable. So please take a read the statement of the theorem. All right. So these are three parts. All right. Well, can I flip the board? Are you okay? Or I'll give you another minute. All right. And the eigenvalue is 0, real part are simple. For example, you cannot have lambda square plus alpha times another lambda square plus alpha. Cannot have that. You can have this one, but not this one, not these two together. So that means lambda square equal minus alpha is repeated. You see? Okay? So this is what it means. All right. So the proof of one, well, we know that e to the at is less or equal to d from before. Now, let xt be a solution of 5.1.1. Then xt is e to the at minus t naught times x naught. Okay? And then this is for t bigger or equal to naught. If I take the absolute value or the norm, this is less or equal to e to the at minus t naught times x naught. Okay? So now, let epsilon be positive, and we need to find delta so that if x naught less than delta implies xt equal to e to the a t minus t naught x naught. Now this is less or equal, this is less or equal to d times x naught, and then this is d, this is epsilon, this is equal to d delta, which is equal to epsilon if delta is epsilon over d. So that shows the zero solution is stable. Okay? Hence, the zero solution is stable. So this proved part A. As for 2, we know xt equal to e to the a t minus t naught x naught. Okay. And so x of t less or equal to e to the a t minus t naught x naught. This is less or equal to d times e to the ct x naught ct minus t naught. I really don't care. All right. But what is psi? You see here, we're assuming real of sigma of a is less than psi, where psi is less than 0, because by definition all the eigenvalues have negative real parts, and then that goes to 0 as t minus t0 goes to infinity, since psi is less than 0. So it is asymptotically stable. Okay. Now it says if there is an eigenvalue of a, so for the 3, let's say the real of lambda I is positive, then part of the solution is e to the lambda I t, which goes to infinity as t goes to infinity. So the solution is unstable. Okay. Any questions? All right. I need you to be careful. See, in the previous theorem, we assumed every eigenvalue is, let me take a look at it, has a non-positive real part, non-positive. Okay. Assume every eigenvalue of the matrix A has a non-positive real part. All right. So in the previous theorem, we assumed okay. So okay, what I want to say is we need to be aware when we have a repeated 0 eigenvalue. For example, if you take x prime equal to and you take x prime equals 0, 1, 0, 0, x. So here, lambda 1 equal lambda 2 equals 0. But the solutions are bounded and x equals 0 is stable. So here, again, we have lambda 1 equal lambda 2 equals 0, but solutions are unbounded. Hence, the 0 solution is unstable. Okay? To see this, take a look here. We have x1 prime equal x2 and x2 prime equals 0. So that means x2 equal constant. So x1 prime equals c1. x1 equals c1t plus c2, which goes to infinity as t goes to infinity. I'm talking about this one here. From the matrix, I can read that one as x1 prime equal x2, x2 prime equals 0. That means x2 equal constant c1. That means x1 prime is x2 is c1 from here. Integrate, you get c1t plus c2, which goes to infinity as t goes to infinity. So here are two matrices, two systems display the same eigenvalues of repeated zeros. One solution is bounded and the other one is unbounded, and hence the 0 solution is unstable. Okay? All right, I will do the last theorem and I will stop for today. Okay? This is theorem 5.15. If all the eigenvalues of A have negative real part, and are distinct, then the 0 solution of 5.1.1 is uniformly asymptotically stable. Okay? Well, the proof is simple. Let real of sigma of A is less than minus sigma minus c, where c is positive. Then we have xt equal e to the a t minus t naught x naught. Okay? Which is and xt is left over equal to e to the a t minus t naught x naught less or equal to k e to the minus ct minus s. Okay, let me so e to the a t minus s, which is equal to phi of t, phi inverse of s, and e to the a t minus s is less or equal to phi t, phi inverse of s. Okay? And this is for t bigger or equal to s. So the results follow from theorem 4.23. So this is very powerful theorem. It says if the eigenvalues of A are all distinct with negative real parts, then the zero solution is uniformly asymptotically stable. Okay? Okay? So we can use the theorem of that matrix. All right, any questions? So that means, so what I'm saying is this is less or equal to k e to the minus of c t minus s. This is the requirement for this theorem. Remember the one we did the example I opened the class with today? So this is what really happened. All right. Any questions? We're doing very well pace-wise. I'm hoping we can finish in the maybe like Tuesday of the final week of class. And I'll give you the final exam then, and you return it to me by Friday of the final week, last week, week number 6. Because the summer session is 6 weeks, not 5 weeks, correct? Or am I wrong? Correct me if I'm wrong. I think it's 6 weeks. You guys know.
I was told 6 weeks.
Yeah, it's 6 weeks. Okay. So basically we have 2 more weeks of serious work, and the last week, maybe Monday, Tuesday, and then I'll give you the final on Wednesday, and hopefully you return it to me by Friday, the latest. Okay? Any questions so far? So today lecture was, last time we did some general theorems, and today we made those theorems specific to the system where the matrix A is constant by only looking at the eigenvalues. So you see how important the eigenvalues are. Okay? They play a major role when the matrix A is constant. But when the matrix A is not constant, everything is off the table. Nothing works. You're lucky if you can find the fundamental matrix solution and then use the general theorems that we have done before. And I have given you good examples. Okay? Any questions? All right, I'm going to stop here. Okay, somebody's saying chat. 6 weeks, okay. All right, I'm going to stop recording unless you have any question.